All right, so last time I very quickly introduced this idea of a computer and how a computer is far more general than what we might be used to thinking about. And like one of the simplest forms, and I'm going to warn you, everything I say is going to be kept at very high level. I'm not going to be precise in my language for the sake of accessibility. I don't want to start overburdening you with jargon and very overly specific things. We're just going to talk about these ideas fairly high level, general, so we can learn a little bit about it. Like for example, you could take a whole course on this one page that I'm about to show you. Like there's a lot more details we can get into. We're not going to hit them all. So, and it's always amusing because like you post these on YouTube and then some asshole will show up and be like, well, how come you didn't? It's like, because this is goddamn first year intro. We spent 1 hour talking about it. So just be warned, it won't be comprehensive. So we first started talking about a finite state machine. It is a very, 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 very simple form of computer. We have like a starting spot, we can have an ending spot, and we can transition states depending on what we see. So this would be an example of a combination lock that needs 773. If it receives any other string that's not 773 string, sequence of numbers, that's not 773, it won't unlock. But if it ever gets 773, it'll unlock. There we go. It's cool. This right here can it can compute. It can determine if the combination was entered correctly. It's capable of doing that. And a stupid little computer like this can do a lot. So when I'm talking about like, oh, the simplest form of computer, that doesn't mean it's not capable. It can do a lot of things. It just can't do certain types of things. So it doesn't mean like, oh, not powerful. Well, no, it can do a lot. It's just it does have limitations that we are well aware of. Let me ask you this. So here I told you this machine, one sec. This machine takes input, 773 to unlock. But I can kind of flip the question and ask you, what type of input does this machine take? But you had a question. How can it do a lot? Well, it can do, there's a lot of like tasks that we have automated that don't require a crazy amount of rules and tricks and whatnot. So traffic lights, there's computers in there. I mean, I'm willing to bet it's a full-fledged computer on a chip, but it doesn't need to be. It could be the dumbest little computing machine there is, more analogous to this, and it'll be successful. Vending machine, combination lock, like a safe, crosswalk thing. There are so many things that just like receives an input, changes state, can produce like the final state, like an output. So very, very simple. So it can do a lot. There are a lot of tasks, and we could spend time naming a whole bunch. But the reality is there's a lot that we do in our lives that requires very little specialness in how capable the computer is. So back to this question, however. We have the starting state, that's the one with the little arrow pointing to it, and then there's a final state. And the question I'm going to ask you is, what are the valid inputs that this computer will take? What are the types of inputs? What are the strings of A's and B's? And a lot of times when talking about like these little computers, we'll talk about these strings of like letters. They're not particularly meaningful in any way other than that we can say, we can make strings that look like this, or we can, like these are the strings that it'll input. But if we change the type of strings, it's not possible to build or change some of the features of these strings. Maybe we can't build a finite state machine that can accept that. So we kind of are using strings to stand in as like problem complexity. That's not that accurate of a way to say it, but that's kind of what we can think about right now. How sophisticated and complex these strings get, maybe these types of computers can't deal with them. So to start simply, I want everyone to take a moment and look at this computer. If this computer here receives 773, it works. This will only accept 773. If we get here and it's any number that's not 7, it just loops back and stays on this state. So if I put in 44444444773, well, that would work because it would just keep looping here and then, 773. So that's, like, this one takes 773, and I showed you, I drew the computer that does it. Here, I've given you the finite state machine, and I'm asking you, tell me what the types of strings, what would the strings look like that can generate this, or that can be accepted by this machine? I said, take a minute and think about it. You can talk amongst yourselves. I don't want the answer yelled out. I want to give everyone a chance to think about it. What do they look like? It looks like you've got some ideas. What do you think? One of you two.
Okay. We said like 4 options, like A, A, B, A, B, 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 A, B, A.
So A, B.
Yeah.
Name another one.
A, B.
A, B. Keep going.
B, B, A.
B, B, A.
And B, A.
And B, A. So you named 4. There's actually an infinite number.
Yeah, but like what's before? Like Z, X.
Well, there's that too, but let's pretend that the only 2 letters it can get are A and B.
Oh. You say them before and then it goes.
Well, what we could do is if we see an A followed by any number of A's, because whenever it sees an A, it'll just keep looping. So you basically had it, but we want to generalize this to say an A followed by any arbitrary number of A's followed by a B will get us there. Also, a B followed by any arbitrary number of B's followed by an A will get us there. And we could actually write these strings down with fancy symbols. And I'm going to try to remember this. This is going way back. I might be writing it wrong. I might be mixing up the two. But what I could write is A plus. I think it's plus. B or B plus A. That is a regular expression. That means the A plus means there has to be at least one A followed by any other number of A's followed by a B. That's what the plus means. If it's a star, I believe it's also allowed to be 0. I might also have them mixed up, but let's not worry too much. So if it was A star, that could be 0 or many A's. This is 1 to many A's followed by a B, or vice versa. So yeah, you were totally right. You had that. So like you named them as 4, but there's also, it's funny, because like this finite state machine can accept infinitely long strings. As long as the last thing is B. I don't care how big the string you give me is, I can make a bigger one that this machine still accepts. Which is kind of neat. So this machine can accept A, B. Or A, B. And so on. I could just keep going. Any questions? I thought I saw a hand. Did you have a hand up? No. All right. Did anyone think of anything different?
I don't know, like, this is an idea. Can you have it so that it has to be A, B, like A, any number of A's and then B, and B, any number of B's and then A, and it needs both of those for it to work?
It needs both of them for sorry, I'm not sure what you mean.
Like, instead of just being able to like go on one path or the other path, having it so you have to go on both paths?
That you have to go on both paths? So you want it to be an arbitrary, like, I'm not sure what you mean, but depending on, there are multiple ways to interpret your question, all of which are interesting. So, do you mean arbitrary number 1 followed by an arbitrary number of A's followed by a B that then has an arbitrary number of B's? Or do you mean it can flip between the A's and B's as it goes?
I just mean there's two, like you need both inputs for it to get an output.
So what I could do is then make it so the final state, yeah, but to have both inputs. I see what you're asking. But what you're asking is that you want, the trouble is in order for you to be specific and ask the question the right way, you would have to be remarkably precise in what the regular expression is that you want. Depending on how you interpret your question, it may or may not be possible to draw a finite state machine that can do what you want. It might not be possible. It depends on how you mean what you want. But I could redraw this such that, like, maybe I take this part right here and just move it after this and move the final state to that other final state. But then it would have to start with A's, then B's. But vice versa, it might be problematic. Because what if I want B's first? Well, then you can switch the order. What if you want it to be able to make a decision? Well, now we're running into some issues. It's a good question. Good potential interpretations of the questions. Yeah?
Can you have like a sort of middle state so that it runs like that or that and then gets to like a middle spot and then it does a different that or that?
Well, again, it kind of depends on what you mean. Like, do you want it to be like, if it started with A's, it has to be followed by B's? Or if it starts with B's, it has to be followed by A's? You know what? We could maybe revisit this. Because maybe your question will get answered as we go. Maybe. So, yeah. What input strings can this machine accept? Well, we just did that. Now think about it this way. Think of how simple the computational system is that is powerful enough to unlock a lock. Computer scientists like to think about what else can this computer do? What else can a computer this powerful do? And that's when I was saying things like traffic lights. Anything that gets input, changes states, and doesn't have to make too many complex decisions can do quite a bit, but there are limitations. For example, I cannot make a finite state machine that can create all possible palindromes of A's and B's. Raise your hand if you remember what a palindrome is. It's like kayak. It's a string that's the same forward and backwards, right? Race car. It's race car. Bob, right? Bob and Bob. So a palindrome is a string that's the same forward and back. So if I wanted the string A, B, A, B, A, B, B, A, B, A, B, A, I can't do that with a finite state machine. Well, actually, that's not true. I could generate that one string with a finite state machine. Any finite string, you can make a finite state machine for it. You just make it however long it needs to be to get to where it goes. So any finite string. But if you want arbitrarily large, like infinitely long palindromes, you're in trouble. You can't do that with a finite state machine, which is trouble. So we can add a little bit of complexity. We can add some extra fancy features to our computing machine. So the finite state machine is the simple little one. But it can do a lot. Now the next one is called a Pushdown Automata. So a PDA, they'll call it. And a similar thing is the context-free grammar. So when we talked about finite state machines, and then I mentioned regular expressions, the analog here is the pushdown automata and the context-free grammars. So now with these types of machines, we can do a little bit more. So they're cool, but they can't solve, finite state machines are great, but they can't solve all the problems there are. In PDAs, pushdown automatons are more powerful computers. I don't mean it has more RAM. I mean it is more capable. It is a computing machine that is more capable. It can do more that the finite state machines can't. They are not, it's not possible. You're running out of batteries? Yeah. There might be a plug by one of your seats. I know some of these lower rows have them. So good luck. So they can solve, pushdown automatons can solve strictly more problems, can accept and interpret more strings than a finite state machine can. And pushdown automatons can accept context-free grammars. They can also accept regular expressions. Anything a finite state machine can do, a pushdown automaton can do, but not the other way around. Here is a very, very, very simple example. This is doing the same thing as the second finite state machine that we looked at. Basically this, the one or many A's followed by a B, one or many B's followed by an A. We can make a pushdown automaton accept this. We can design our pushdown automaton to do that. And here's how I would describe it. The S is like your starting condition. I would start by just having an uppercase S. And the convention here is the left-hand side is like what we're currently looking at, and then the right-hand side is a decision we can make. See how there's lowercase and uppercase letters? The lowercase letters are the letters that are actually parts of the strings that we care about. The uppercase ones are for the rules. So in uppercase A, we have those rules. So let's start this one, for example. I see an S. So if you look at those set of rules, what are my choices I can do with an S?
Lowercase a, capital A, and lowercase b, capital B?
Exactly. That's it. If I see an S, I can replace the S with one of those two things. A, or B. Uppercase B is more excited. So I can take this S, pick one. Who wants the top? Who wants the bottom one? All right, we're tied. We have one vote and one vote. Let's go for the bottom one. All right, you had a question.
With the capital S equaling like lowercase a, uppercase a, can you substitute like the third thing on that list of the uppercase a with lowercase a, uppercase a? Am I thinking about this wrong?
I'm sorry, ask that question again.
Like for the first thing, like if that was a list, for the first item in the list, when S goes to lowercase a, uppercase a, can you sub the third item in the list, lowercase a, uppercase a, in for the uppercase a in the first item in the list?
Well, effectively, yes. So here's what I do. I look at the S, and then I can replace S with, we were going to go with the second one, B. So I'm going to replace maybe this. No. What the? Yeah, it's whiteboard marker. It even says whiteboard. All right. Maybe I won't use this one because it might be lying.
Yeah, that's my question.
So I'm going to replace the S with the lowercase b, uppercase B. Great. Now, I see an uppercase B. That means I can apply any of the rules that contain an uppercase B on the left. Which one do we like? BB. Great. So I'm going to replace the uppercase B with B uppercase B. Let's see. Will this work this time? A. So I replace that B with B, B. Now what do I want to do? Do it again. All right. I'm going to run out of room soon.
And then do the
B uppercase B.
A. Now do A.
Now do the last one? No?
Keep going.
Keep going. Well, we can forever.
I like this idea. We have room for one more. Let's do another one.
All right, fine. I'll just do it in one go. There. There. Great. We can do that. And as you can maybe see now, following these rules, you can pick the order of these rules to follow, and you will generate any string of one to many B's followed by an A, or one to many A's followed by a single B. Those set of rules will generate those things. But I can ask another question of, here is a whole bunch of strings. I want you to tell me what the pushdown automaton set of rules need to look like. We're not going to do that right now. That can get pretty hairy. But there we go. This pushdown automaton, or automata, well, automaton because it's one, can generate any of those things that for that first finite, or that second finite state machine that it can do as well. Are there any questions about that? It's important to note that the lowercase a and the uppercase are different. So the uppercase is like part of the rules. The lowercase is like 11 in the string from the available symbols we can use. So yeah, any questions about this? All right, what do I say? Uppercase letters, special symbols, lower. Yeah, okay, cool. So the trick here is start with S. We have two options. Let's go with the first. And whatever, I'm just doing an example. So here's another one. I want you to tell me, so epsilon means like nothing. Replace the S with literally nothing. So it's a way to stop. I want you to take a minute or so, think to yourself, talk amongst yourselves, what types of strings can this pushdown automaton generate or accept? And I want you to not, like, I don't want you to just give me one or two examples. I want you to try to generalize and explain to me what those strings would look like. When in doubt, do a couple examples on your own and then see if you can generalize from those. It might help if you start scratching it down on paper.
No. That's how it's fake. Oh, you're right. Yeah, you're right. It's nothing. Yeah, so it's just like whatever. And then,
Well, how they're the only ones discussing it.
Well, people might be thinking about it. Why aren't you discussing it? All right. Raise your hand if you've got an answer. What do you think?
Like a palindrome, like saying forward and backwards.
You are very close. But there's one little difference, one little special thing you also have to include. Is your hand up?
They can create palindrome, they can create the every
False. That's what he said.
Yeah. I'm trying to work this out.
It's whichever combination of A and B, and then the exact same thing mirrored.
That's a pound. That's what he was saying. There's one. You are all like 90% correct, but there's one other special important fact you gotta include here.
There'll be like an empty.
Well, the empty is like nothing, so we don't worry about the empty being in the middle. Come on, do you not see it?
I just say that doesn't create every possible one.
Well, which ones can't it create?
It cannot create ABA.
ABA. So can you generalize what you just said?
They can create any even length palindrome of A's and B's.
There you go. It has to be even length. But I want you to take a second and think about this finite state or this pushdown automata. Look at the set of rules we have and see if you can come up with a modified version of these sets of rules to be able to generate odd length ones. There are a couple ways to do it. It sounds like there's an idea over here. You got it?
You could have two more things for S, which would just be A.
Exactly. Create two more rules that say S can also go to just a single A and S can go to a single B. That's all you would need to do. And then suddenly it can also generate the odd length ones, which is pretty cool. But you want to know something that this can't do? If you wanted to have like, it's going to be similar. If you wanted to have like X A's followed by X B's followed by X C's, the same number, you can't do it with one of these. You can't. It's not possible. It can't do that. Which is kind of funny. I mean, this can do more. The PDAs can do more than the finite state machines. They can. But they can't do everything. They're strictly more powerful than finite state machines, but it does have some shortcomings. So here's another PDA. I want you to tell me what this can generate. I'll give you a minute to think and talk amongst yourselves. It's not too different from the one above. Don't worry about what? This problem? You should worry about it. All right, who has got ideas on this one? Raise your hand really high. Let's go with you. Not you, him.
I am also not very confident.
Well, let's hear it.
So first option just creates an infinite number of S's. The second one encloses every S in brackets, and then the third one will remove all the S's and just double bracket each of an S in brackets.
So you've described the rules great, but what do the strings have to look like? Let's see if you get other people trying. Raise your hand high if you've got an idea. You answered a previous one, though.
Oh, awesome. I'll answer the previous one as well, if you want me to answer that. Go ahead. Okay, it creates any combination of closed brackets. Of open closed brackets. In basically any order. Well, as I can tell. I think it might be this one, but I believe it does give every combination.
Yeah, you can generate any possible combination combination of valid open-close parentheses. So with this, it would not be possible to have like an incorrect number of parentheses. For every open, there's a close. But they can nest inside each other, great. And there can be like two nested ones beside each other here with many down. It can do that, but it'll always have an open with the close. There'll never be like, there will never be a dangling open or anything, or an extra close. It has to be correct. This little machine, you know how when you're, well, I guess you don't in Python. Well, never mind. So there you go. This can generate any valid sequence of open and close parentheses. Cool. It's pretty neat. Now we can go a little bit further and talk about even more powerful things. There are context-sensitive grammars. Context-sensitive grammars we can describe like this. And to be clear, the one above, we were talking about pushdown automatons. These set of rules aren't the pushdown automatons. They are a definition of the context-free grammar, but they are equivalent, so just to be more specific. So context-sensitive grammars. There's just an added extra little bit of rules to how we do it. Basically, we add context to the rules that we can use. What I mean is, we start with an S, but see how like we have the uppercase letters on the right-hand side? But for example, if you look at the second rule of S, A, B, C. See how there's that uppercase A? Now, when I go look at the set of rules, I'm only allowed to pick one that has a matching set. So it looks like the only possible rule I could follow is the uppercase A followed by a lowercase b. So it adds context. It adds context to like what character is allowed to be beside it, or must be beside it. So it's just an added extra level of complexity to these computing machines. But with this extra little added level of complexity, we can do even more than we couldn't before. So I want you to try this one out. And for this one, I'd recommend sheet of paper and a pencil, because they're starting to get too complex to be able to do in your head. Sheet of paper and a pencil, and scratch this one out and see if you can figure this one out. Give yourself a couple minutes. This is a good one. Raise your hand if you have an idea. Really high. I want to see if you've just got an idea. You don't have to be that confident in your guess. I just want to know. So what do you think? The person in front of you. You. So it switches the values. So you're I'm not sure if what you mean is quite correct, but your brain's going the right way, that's for sure. Raise your hand really high. I want to see. What do you think? Him. You. No. Yes.
Oh, I think it creates an infinite amount of A's on one side and an infinite amount of C's on the other side, separated by a B in the middle.
An infinite number. Can you be slightly more specific, though?
Because like if you keep doing it, it keeps looping over, so you keep adding more A's to one side and C's on the other, but the end of the B has to be in the middle there.
Mm-hmm. So you're right, but there's like an added extra little thing we got to include on there. What do you say?
It'll create an equal number of A's, B's, and C's, but there can be any number of those things. They just have to be the same number.
Exactly. So this was that example I talked about a moment ago. How you cannot, there is no context-free grammar that can generate those strings. Any number of A's followed by any number of B's, but the same number, followed by the same number of C's. You can't do that with a context-free grammar, but you can with a context-sensitive grammar. So this is strictly more powerful. But once again, there are certain problems that you can't solve. There are certain strings that you have no hope of getting with this. There are certain things you just can't do. For example, this computer cannot play Doom. It can't. But this can. This one can. Turing machines could. A Turing machine is fantastic. Turing machines are like these computers. The definition of what a Turing machine can compute is the same as all of those other computers. Your computers are computationally equivalent to Turing machines. Obviously, it doesn't look like that, and we're not going to go into the details of what a Turing machine is, because it starts to get a little bit more like nuanced, which we don't really have the time to go into. But Turing machines can do that much more, and they can deal with like fancier strings that other ones can't. So this can play Doom. Anything that is computationally equivalent to a Turing machine can play Doom. It can. So all of these computers that you have here they're equivalent to a Turing machine. So a Turing machine can deal with regular expressions, the finite state machine stuff, context-free grammars, context-sensitive grammars, and their own stuff. And they're like the most powerful model of computing. Raise your hand if you've heard the name Turing before. Of course you have. So this is named after Alan Turing because it was his idea, but originally he didn't name it. He didn't name it after himself. But yeah, anyone know of any other things that is named after Turing? Turing test. What else? That he didn't name after himself. He called it the imitation game, and then everyone renamed it to the Turing test. What else? There's a lot. Computer scientists are obsessed with him, rightfully so. And as a consequence, we've maybe gotten a little overzealous naming things after him because it can get a little confusing. But Turing machines are a very high form model of computation. It's strictly more powerful than all the other ones that we looked at. Now, they're not like this computer, it's not built like the Turing machine. It's got a different architecture and design that we're not going to get into. but it's based on the Turing machine. And the interesting thing is I was talking earlier, and a bunch of students last week when I was like, can you point to a computer? A couple of people pointed to themselves. Yeah, absolutely. You are at least as powerful as a Turing machine. But we are careful to say at least. Because the trouble is, we have a lot of open problems in computer science. There are a lot of questions we don't have the answer to, such as, is there a better thing? Is there a model of computation that we can define that's strictly better than Turing machines? We don't know of one. Maybe there is, maybe there isn't. We don't know. Maybe we are more powerful than Turing machines, but we just haven't come up with a way to prove or demonstrate that that's the case. So we are at least as powerful as a Turing machine. Anything this can do, you can do. But we're not sure if there's stuff we can do that it can't do. Raise your hand if you found these ideas interesting, at least at a high level. It's kind of fun to think about this stuff, but these ideas are the core base principles of computing. And if you really did find this interesting, and you want to learn a lot more, presented in a really good way, I highly recommend a book to you. It's a Pulitzer Prize-winning book written in the 70s called Gödel, Escher, Bach, An Eternal Golden Braid or something like that. There we go. This book, except it's got a newer, this one. It's in English. There is no programming language. Gödel, Escher, Bach. Oh, if you're wondering, those are names. Yeah. So they're named after people from other parts of the world. Right. So Gödel, Escher, Bach. Oh, look, see, I bought it on 2016. How about that? So point being, if you're interested in this stuff, have a read of that. Anyways, see you later.